Shown in the figure below is a simple yo-yo. The body of the yo-yo has a radius, capital R is 0.04 meters, and the shaft that the string wraps around has a radius of lowercase r is 0.002 meters. Approximate the yo-yo as a solid cylinder of radius capital R and mass 0.1 kilograms. At this point in the problem, we can't yet choose between force methods and energy methods as the route to get the solution. We need to consult the questions. Part A, we're asked what is the downward acceleration of the yo-yo, and Part B, we're asked what is the tension in the string. These questions resolve our choice. Energy methods would relate kinetic to potential energy, and so if we have been asked what velocity we achieve after falling a certain distance, energy methods would be the most appropriate. However, since we've been asked for acceleration and tension, force methods are indeed the most appropriate. The first step in any force problem is to draw a free body diagram. There's only one object, it's the yo-yo. And when we draw our free body diagram, we will be drawing an extended free body diagram because the yo-yo not only experiences linear motion, it also experiences angular motion. The first force we imagine is m times g, and the gravity force acts at the center of mass of the yo-yo, which is right in its middle. That is of strength 0.1 times g. The next force we see is that of the tension. The tension acts at a radius lowercase r away from the center, and since tensions always pull, the tension is pointed upward. That's it for our entire free body diagram. The principle by which we orient the coordinate system is, as always, with the acceleration. The yo-yo will be accelerating downward, so we will make that as the plus direction, and the yo-yo will be accelerating clockwise for the rotational motion, and so that's what we'll be making as the plus direction for that. This problem will produce one linear equation, that's in the vertical direction, and it will produce one angular equation, and that will be in the clockwise direction. Let's begin formulating those two equations that will lead us to our two answers. We'll begin with the vertical direction. Since we've chosen downward as the positive direction, the gravity force will be our downward or positive contribution, and the tension will be our negative contribution. The sum of the forces, as always, is equal to the mass times the acceleration. This equation has two unknowns, and therefore we place a box around it, saving it for later. The second equation that we'll develop is in the clockwise direction, and rather than a force equation, this will be a torque equation because this is an angular direction. When we examine our forces that create torques, the first thing we recognize is that the gravity force does not create a torque. If you imagine that the yo-yo had nothing but gravity operating on it, i.e. you removed the string, the yo-yo would fall directly to the ground and would neither accelerate clockwise nor counterclockwise. It is because the string has been placed away from the center of mass of the yo-yo that the yo-yo will in fact have an angular acceleration. Therefore, it is the tension that formulates a torque, creating the angular acceleration. This T does represent the tension force, but since this is a torque equation, T is insufficient. We must multiply the tension by some radius. And in this problem, we have a choice of two radii. We have the lowercase r, which is the radius of the shaft around which the string has been wrapped, and we have the uppercase r, which is the entire size of the yo-yo. Since the definition of torque asks us where any given force is applied, we recognize that the tension force is applied at a distance of lowercase r, and therefore this is the appropriate way to complete the torque due to the tension. As we said, gravity creates no torque, and so we have the total torque is tension times radius, and the sum of the torques, as always, is I times alpha. Examining that equation, there are two terms that you like a little bit less than the others. These are the moment of inertia and the angular acceleration alpha. Each one of these is a formula that we can write down easily. However, we're going to need to keep in mind which radius we need to use for each formula. Let's begin with the moment of inertia. Since we're asked to approximate the yo-yo as a solid cylinder, we know that we will have 1/2 mass of 0.1 times the radius squared. Which radius should we use? Well, since the moment of inertia accounts for the fact that the mass of the yo-yo is spread over a certain region, we clearly would use the larger radius, capital R, because that is the one that is related to how broadly the mass has been spread throughout the object. However, for the angular acceleration, let's look back to the figure for a moment and see if we can understand that. The relationship between angular and linear acceleration has to do, in its derivation, with an object that is rolling. When we envision the system, including the yo-yo, what we can see is that the yo-yo unrolls the string, and it unrolls the string using a radius of lowercase r. Therefore, when we fill in our angular acceleration formula, we will use lowercase r as the ratio between the linear acceleration of the center of the yo-yo and the angular acceleration of the yo-yo spinning around its own center of mass. Plugging in all of this information into our equation yields the following result. As compared to the simpler yo-yo problem performed previously, the radii do not cancel. However, we can make a simpler expression out of this by first doing the arithmetic with the numbers, and second, grouping the radii into a single factor. That expression looks as follows. One further simplification will be to plug in the values for the large radius of the outside of the yo-yo and the small radius of the shaft itself. And this yields the simplest formulation of the equation itself, which is that the tension is 20 times the acceleration. And this is our second equation that we place into a box. To finish out the algebra, we need to group together the two equations within boxes and then solve them out. We notice that the principle of the tensions continues to hold. The tension appears once with a plus sign and once with a minus sign, and therefore the simplest solution of these is to simply add the equations both to the left and to the right of the equal sign, yielding 0.1 g on the left and 20.1 times the acceleration on the right. This yields an acceleration of 0.0488 meters per second squared. To solve for the remaining unknown, we plug this result for our acceleration into the simpler of the two equations, which is the top one, so that the tension, being 20 times the acceleration, becomes 0.975 newtons.